Hoon School HSL2. Okay, this is trees and addressing and how all of that works. So you got some of that last time in taking a look at how everything in Hoon is a binary tree ultimately, but you can also think of runes, even runes with more than two children, as being runes that have multiple components down. So what we're interested in today is ultimately, okay, so computers were built and designed to carry out tasks that humans don't want to repeat consistently, right? They were originally built to solve differential equations for nuclear bombs, and now we use them to solve gigantic matrices because we want to see slightly blurry pictures of deformed things that show up in an AI. But what we want to do, so at this point, essentially, we don't know how to make the program solve lots of things over and over and over again, right? We don't know how to do anything that looks like what in other programming languages you would call looping or recursion, but is essentially this idea that you can keep executing a certain block of code over and over again with slightly different changes to its inputs, right? And perhaps based on previous runs, perhaps based on a new entry in a list, and so forth. We kind of know how to do that because when we write a gate, we're giving it a definition that we can use in for a deferred calculation, right? I can reuse that piece of code again and again and give it different values when I step in again. There's a question here about, okay, so the new Hooniverse group is up and running. Hit up Danet/new Hooniverse. If you've missed the first couple of classes, then go ahead and check out the YouTube recordings and get in the group, and you will be able to find the lesson notes and the homework as well. We had the quick response for the homework, the first homework sent back already, but you can continue to submit it until I think it's going to be like a week and a half after the end of Hoon School. So there's a window to be able to go ahead and join that still. All right, I'm going to go ahead and share.
Sorry, quick question.
Yep, go ahead.
I started basically right after the first class. Is there a way to receive the first piece of homework?
Go ahead and join. I think in the Hooniverse group in the Hoon School live chat, I believe I posted the contents of both emails. You may have to go back a couple weeks in the chat to find them because unfortunately you can't pin things easily. Yeah. But the links to the homework and everything should be in there. If you can find the notes, then the notes will have a link to everything as well, included in the notes.
Thanks.
Okay. All right. So right now, you know how to write Hoon code that makes a decision between two different Hoon expressions. We can think of it as, we start our generator, we load our gate, like whatever, right? Like generator is the file that contains a gate. There are other kinds of generators, so we can't say the generator and a gate are the same thing because they're not exactly the same thing. But right now, the only kind of generator we know how to write is a gate. So it's a function. So we start our function, we set A and B as inputs here. And then we have a decision, right? But based on the values of A and B, we can execute, or we will, in this case, I can say we execute an expression, but because of what Hoon is, in this case, it just returns the value that arises from just evaluating A or B. So this is a pretty trivial function here where it simply says, is A or B larger? And return the one that is larger. So it's not returning true or false, like greater than is. It's sort of it's like a max function. It's returning the greater of A or B. And we can have more complicated expressions in either of these branches or one of these branches and not the other. Those are options that we have available to us. But right now we're just looking at this. So computers can decide between alternatives, but we also want them to be able to carry out a task until some condition is met. If we're thinking of this in recipe terms, we could say something like, if a recipe includes 5 eggs, that's listed. I guess you're making a quiche or something that has a lot of eggs in it, but it includes a lot of eggs, and so this is shorthand for you to crack 5 eggs in a bowl. And so for you as a human, that this process looks like you get 5 eggs, you grab the first one, you crack it, you dump it in the bowl, you throw the shell away, right? There's this processing step that takes place. And you repeat this processing step for each item. You carry out this equivalent action on the next item or the next element. In a computer program, we call this a loop. So it describes the situation in which we set up some condition and we repeat a process over and over again until something we do meets that condition. So, in the case of the eggs, we're basically saying until we get to 5 eggs, we're going to continue grabbing an egg, breaking it, doing whatever our process is, our expression is. So we're going to be continuing to process those forward. Now I'm going to try doing a direct switch in my share, which has a mixed track record for people. So if you can't see this, let me know. Sometimes Zoom doesn't like to do this. Sometimes it does. All right. So let me go ahead here. All right. So we have let's add a counter. Let's create a sum. So something that we're going to add things up into. And actually, let me make this slightly larger here. And all right. So I'm going to introduce a new rune. This is called a bar hep. And we're going to call the structure that it defines a trap. Right? Now, the first thing we put in, this is like a for loop if you have run into these in other programming languages. If you have not seen something like this, then we'll talk through what's going on here. Everything in Hoon needs to ultimately result in a value. Any expression you write needs to result in a value. So I'm going to go ahead and write this out where the first thing we're doing here is a test on whether or not our counter is greater than 5. I will give you all the code in just a moment, so you can type along with me if you like, or you can wait until I paste it, and this will work for you. And I'm going to introduce a sentiz rune. And I'm going to tell it to add 1 to the counter. And I'm going to tell it to add counter to sum. And then I'm going to close that clause out. All right, let me share that code with you. And put it all visible down here as well. All right. What this program has done, ultimately, it has basically added 1 plus 2 plus 3 plus 4 plus 5. And then because counter at that point is equal to 6, that wouldn't evaluate, and you would just get the result 5 plus 4 plus 3 plus 2 plus 1, which is 15. So 15 is the result that comes out of this expression here. How does this work? What's going on here? We're gonna come back to this concept more in either the next lesson or the next 2 lessons. So right now I'm going to give you the very mechanical description of what's happening. And next time we will go deeper into why it happens some particular way. So in a sense, if I'm writing a kind of a code description of what's going on here, my first time through this loop, when I reach this trap, the first time I evaluate it, my values are counter is 1 and sum is 0. I just define them on the line above. And so that remains true. And so then I do a test and I say is greater than counter 5. So is counter greater than 5 at this point? You can answer if you like, but should be obvious here that counter is not greater than 5. So this is Hoon's false value. I'm using the colons as the comment there. So this is Hoon's false value is sen n for no. Because it is not false, this first branch is not taken and the value sum is not returned. So instead, whatever this weird thing is calculated. Okay, so we have a cursor in the right spot here. Let me add a new, there's a sentence ruin. I'm going to call this a reset. Okay. What this does, and we're gonna hand wave a little bit about this dollar or buck symbol right now, but these go together for now. What this does is it takes a set of changes and then it returns to this point in the code having made those changes. So in this case, what it will do is it will counter will become counter plus 1, so it will become 2, and sum will become 0 plus 1 will become 1. Okay, does anything surprise you about that? One thing may surprise you, which is, didn't we just change counter when we add counter to sum? Like if I'm working in a language like Python or JavaScript, it matters the order that I say these things, right? If counter has already changed to 2, then in Python you would expect this kind of operation to say, well, okay, now sum is 0 plus 2, and sum would result in 2. So this entire collection of changes that is given to the sentence, to the reset rune, takes place simultaneously. So it doesn't know about the other changes that are being listed here. It's just that the value of counter will be replaced with the expression to its right. The value of sum will be replaced with the expression to its right. So then when we come back in, now we do a new check and we say greater than counter 5. What's my answer now? Has anything changed yet? Something's changed. What's the value of counter now?
Would it be false?
Okay, so it's still false. It's the answer's, the counter is 2. 2 is not greater than 5, so it's still this. And so we evaluate the line that would say counter to 3. And then the sum would become 1 plus 2, which would become 3. All right. So we can continue this. We can go all the way down, but what's ultimately going to happen is we're going to reach a time when let's say we do counter. Let's do counter. So 5 is still no. So counter becomes 6. Sum becomes, I guess that would be 10 plus 5 becomes 15. And then at that point, greater than counter 5 becomes true or Y, yes. All right. So when that happens, what results? At that point, it takes the other branch, which is sum, which is the value of 15. And since sum is a simple result, it's the end of an expression. That's the value that gets handed back out of this entire data structure. So this entire data structure is evaluated over and over again, or what we call a loop, until it results in a particular atom or noun or whatever. It results in a noun, an atom or a cell. And then that value is handed back out. And since that value results in 15, that's what I get out here at the other end. All right. Questions about this?
Yeah, let's say you have a loop like this and you want to debug it, and you want to, there's no debugger tool, and you want to just print counter and sum to the console at the end of each iteration through the loop. Is there a way to do that?
Yes, there is. Let me see if I have an example. I do have an example. I'm actually going to simplify it just slightly because I think it's not well written. But I have only myself to blame for that. All right. So let me give you this code here and then evaluate this code. All right. So what has changed in this code that I just wrote? Besides the fact that whatever I typed here didn't evaluate correctly. I have more trouble with getting spaces right on these things.
Looks like you've
All
got
right.
printfs going on.
What's that?
This looks like you've got some printfs or equivalent going on.
Right. So
Yeah.
these are called SIGPAMs. Anything that starts with a SIG rune is basically, it's sort of like an aside to the runtime. It produces a side effect. And in this case, the side effect is that it produces output. Okay. So it's going to print the word counter and then the value of counter, and then the word sum and the value of sum each time through this loop. One question for you here. How many children does SIGPAM have as a rune?
It would just be one, right?
This is a print statement. Look at it again. How many children does it have?
Do all the runes that follow after it count as
Yep,
children?
it has two. It has two children. One of them is the thing that is going to be displayed, and then the rest of it is the rest of the expression. And I point this out because sometimes you try and do something like, oh, I want to print a message here. And then what did my dojo do?
Nothing.
My dojo is waiting for a value, right? Like an expression doesn't close until it results in a noun. And there is no noun here. So a SIGPAM has two children. So in this case, I type 0. So 0 is what's ultimately returned out of this expression. Now, there are other ways that we can set up loops. All of the loops that we are going to write at this point in Hoon School are going to be very close to this structure, where we start our loop, we start our trap, our point of recursion. And the reason we call it a trap instead of a loop is because it's sort of like it's the trap, it's the point we return to. But there are other kinds of ways of building loop kind of structures. There's other ways to do this. So like a gate isn't exactly a function. Function is not exactly a gate. They don't map one-to-one to each other. So here a trap doesn't map one-to-one with a loop, and there's other ways of doing looping kind of structure. But we're gonna have the bar hap at the top. Then we are going to have a test of some kind. Typically, we're going to use a counter. You don't have to use a counter. This is like if you're used to C or Java or something. This is like just saying for int I equals 0 and so forth, right? Like it's kind of a primitive way of counting. Like there are more sophisticated ways to do this. Like do it once for every item in the list, and I don't have to ask you how many items are in the list and count up to that number. There's nicer ways to express it, but for right now, we're going to stick with this because I think it's more intuitive to just look at the raw number. So there's going to be the bar hap, there's going to be a test. One of the branches of that test is going to result directly in a value, and one of them is going to result in some sort of reset statement that's going to change the values and then go back up to the trap and continue to evaluate. Okay. We're going to do a lot of these, so you're going to get used to this. Now, the how many children does a bar hep have?
One.
It has one. Why does it have one?
It's just the child rune that it's going to execute.
Yeah, right. It's just the expression after it, right? There's one expression after this. It has a lot of sub expressions. It has a lot of pieces inside of it, but a bar hep has one child. Yeah, we'll make the video. We'll make the video available because yeah, you may want to pause and type different versions of this code out and see how it behaves. So also briefly, let's go back. How many children does a TISFAS have? It's not two. It's three. Right, it has a name and a value that are injected into our expression, and then it has the rest of the code. Don't forget about the rest of the code, because if you do, you end up with this situation where you have like a hanging problem. Did anyone run into a generator build fail error when they started working with generators? If you haven't, you will. A generator build fail is, it's sort of saying there's a syntax error, there's a problem in your code. One of the most common problems is to miscount runes and end up with like, there's either too many children to something, or there's a dangling child you're looking for, and like there's no child rune there. Like if you ended a file with TISFAS counter 1 and there were nothing after it, that would give you a generator build fail, because there's no way for that to be evaluated as valid Hoon. There's something missing. Part of it's not there. All right, let's do a factorial. A question here. Could you explain the increment in counter to 2 while sum is added by 1? So you're talking about basically these lines right here. Is that correct? Okay. The changes in the send_tis statement take place simultaneously. So the change to counter and the change to sum, like all your changes are listed, and then they all take place at once. Think of it that way. So when counter is used in the sum statement, it's still the previous version of counter. Yeah, Jack's over here talking about basement universes or something. Sure, there's your hard sci-fi for the day. Yeah, so the values of counter and sum used on the right-hand side over here are the values that they inherit from upstream in the code. I mean, it'll happen with a copy of the value, like whenever this expression is actually evaluated in Hoon, but you as a code author don't really need to think about the mechanics of it, other than counter has not changed when you use it in the second line here. All right. Clarified? Are we happy with that? All right. So let's do another version. Factorial. Computer scientists love factorials. They calculate them all the time, right? So factorial is saying something like this, right? Where we have a number and we're going to calculate the multiplication of all the decrements of this number together. So I'm going to show you some code. It's a little bit more complicated, but let's talk about it before we. I really need to figure out how to turn on syntax highlighting in my Hoon instance here. Let me give you that code there. So this code that I have highlighted here, this code is a gate that will calculate a factorial. So let's talk through line by line what's going on and figure out, validate for ourselves that this makes sense. So it's a bar tis that takes a pat UD, it takes an unsigned decimal number and it gives it the name n. The only thing it has inside of it is a trap. This trap is going to print the value n to the screen. It is going to ask if the value of n is 1, in which case it will return n. It is going to multiply n times, okay, so that senless there, that is to multiply two values together. So a senless has 3 children, it has a gate and 2 children. So if I were to do it here, senless mul 3, 4. So you could think of it, like, we know there's a lot of ways to write these equivalent expressions here. We saw this with coals. It's true with sens as well. So there's a lot of equivalent ways. You don't use most of them very often, but they're there. So it's going to multiply the current value of n times, here's the reset rune again, times the result of decrementing n by 1. This one's a little bit more complicated. All right, so we are going to run this down. Let me actually save this in a generator just so you are seeing my process for that as well. So prompt off. All right, so CD Zod. All right, so base is one of my, sorry. So remember, you have to do bar mount base. I've already mounted it, so it's going to give me the already mounted error. And then you're going to use some text editor to interact with it. And we're going to put whatever we put in base gen. And there's a bunch of Hoon things inside of it there. I'm going to use VI. If you haven't used VI, don't use VI. Because the most commonly searched question on Stack Overflow is, how do I exit VI? Because there's no menu if you do this. So VI is a command line text editor, but it doesn't give you a menu or anything. You just have to know what the commands are. So people get stuck there a lot. So I'm going to paste the code that I just had. I'm going to save it with the name factorial.hoon. You can do this in VS Code. You can do this in TextEdit. You can do this in Notepad, whatever you want to use, it's all fine. I'm going to bar commit base to tell Mars, to tell Urbit that this file's there, and it should tell me, okay, yes, so it sees a generator called factorial Hoon. And now I will run it by giving it a value like 6. Okay, so it's going to print every time through, it's going to print the current value of n. And then if n is equal to 1, it's going to return n. Otherwise, it's going to keep counting up this way and do this multiplication. So it sort of like walks all the way down this tree and then walks all the way back out. So it goes from 6 to 5 to 4 to 3 to 2 to 1. It's got to 1, the value is returned. So now it can do 1 times 2 times 3 times 4 times 5 times 6 back out. Not necessarily the most efficient way to calculate it, but it works here. It does what we want. Take a look at this code over here on the right or the left, because they're both here on the bottom. Are there any runes that you do not recognize here, or any irregular expressions that you do not recognize here? All right, so senless is a form of writing an expression. It's going to do an evaluation the same way that senhep did, but it takes 4 children. It takes a name of a gate. It takes the first argument to the gate, the second argument to the gate, and then the rest of the code, right? The rest of your expression. So it's going to run it takes 3 children because it results in a value. It doesn't have a rest of the code. So it takes 3 children, it takes the name of the gate, and it takes 2 arguments to the gate. So it's going to multiply 3 times 4. So it's equivalent to this statement here. These two are equivalent statements. They're written with different runes. And let's see, SIGPAM is going to be our display, our print rune. What about this? No one challenged me on this. What's going on with this one?
Is that a shorthand for equals?
It is a shorthand for equals, and it's actually a rune that is .tis. So .tis55 is correct. You almost never see it in the form .tis. It is basically always used this way, but now we have another rune. Let's see, so we have Sunless, gate with 2 args, and we have a .tis, which is an increment operator. So there's an increment operator, or no, sorry, this is an increment. This is a equality check. Yeah. All right. The CENTIS bit here. Okay, so this is our reset rune that we introduced in the last one, right? So this is going, what this is saying collectively, this line CENTIS buck. No, sorry, Jack, I'll talk to you in a second. So we have CENTIS buck. What CENTIS buck does is it applies these changes and goes back up here to this point. So the first time through, and as the value 6, we print 6. Is 6 equal to 1? No. So we come down here and we multiply 6 times. What happens if we decrement 6? So the 6 is set aside, and then this entire trap expression is reevaluated with the value 5, with the decremented value. So then it goes all the way through, and it sets the 5 aside, and it decrements the 4. It sets the 3, it sets the 2. So these are all set aside, 6, 5, 4, 3, 2, and then it gets to the 1, and the 1 value does evaluate, does return, and so 1 gets returned, and then we do 1 times 2 times 3 times 4 times 5 times 6, all the way back out. What tis is a type equality, not value equality. So .tis is for value equality. All right. 905. All right, let's see. I think we're okay here. We need to talk about lists and trees, because it turns out that an awful lot of things we're going to do in our lives deal with lists and trees and addresses and cores and all that fun stuff. The core is like this main idea in Hoon that we're going to work with. Let me switch back to the slides briefly. It's the right one. Okay. All right. Here is a tree. It is a beautiful tree. It is a binary tree. Why is it called a binary tree? At each point, it branches into two values, right? So it goes from 2 branches to 4 branches to 8 branches to 16 branches to 32 branches to 64 branches, all the way down. And so this is a tree. Now, computer scientists at some point in the past decided that trees should be upside down. So they normally write upside down trees, which is a little bit frustrating, but here we are. Whenever we talk about any code in Urbit or any data, and we want to access part of it, any arbitrary part of an expression, we have 3 ways of accessing that value. We can use the numeric address, which follows this scheme here. It's useful when we know the address. It's like knowing a room number or a street address directly. You know the value you want to get. The positional address is another way of writing this, and I'm going to give you the preview of that here. You write them with heps and gals and lusses and gars as you go left and right. It's a little bit strange, but it's readable once you get used to it. And you never do like the deep stuff using positional addressing. This is like knowing the directions to a house, even if you don't know the address of the house. Go down the road, turn left at the 2nd street, and so forth. And then there's what's called wing addressing. And wing addressing is what we're doing anytime we attach a name to a value so that we can access it directly. So when we're doing a TIS-FAS, we are giving a name to a value, and then we're able to look this value up later. Some subtle differences between that and wing addressing, but we don't need to worry about that here. Basically, you can give it a name. You know, this is Jack's house. You can give it a numeric address. It's, you know, 123 Sunnyvale Lane, or you can give it a positional address, which is saying, you know, it's the second street over, third house on the right. Okay, so any of those ways we can use to access particular values here. What this means in Hoon terms. Let's go back to our fake sod. All right. Yeah, you don't live on 123 Sunnyvale Lane. Let's see. Let's do. All right. So if we're going to address something numerically, that is terrible, and I should call these A, B, C, D, E first. Okay, so I have this value. I'm going to pin it with a face for like this for Dojo, so I'll be able to talk about my nums without having to include a TIS-FAS every time. But as you'll recall, this is a Dojo convention, and you'll have to use a TIS-FAS if you want to do this inside of a generator. All right, so if I want to look at what is inside of my nums at address 2, it tells me it has the value A. And if I want to look at address 1, it tells me it has everything, okay. And if I look at the value 3, it tells me it has B, C, D, E. Okay, so what this means here, let me go back to my tree diagram. Let's go to this version of it here. All right, so what this means is that when I'm storing a value in a cell, the value on the value over here, I guess that's a single image. This 2 is the head of the cell, and then the 3 is the tail of the cell. It's everything else in the cell. So a cell is a pair of 2 values. So there's a head and there's a tail. There's a first value, there's a second value. The 2 refers to the head of the cell. The 3 refers to the tail of the cell. So in my case of A, B, C, D, E, A is first, B, C, D, E is everything else. If I go to 3, then I see B, C, D, E. So if I were to ask it then, what is it the address 6, the head of the cell B, C, D, E, what would it tell me? It's the head of B, C, D, yeah, it's B. What's the tail of B, C, D, E? It's C, D, E, right? It's not just E, and this is one you got to be careful with. It is C, D, E, it's the entire rest of it. This is a Lispy kind of convention here. So the head is only the first element, and the tail is the second element because cells only have 2 elements, but the printer doesn't show the brackets all the way to the right, which is a little bit confusing when we're at the, yeah, thank you, Samuel. So that's what's going on here. If 7 is CDE, what is 14? So 7 is CDE, 14 is C. What is 13? Let's find out. Let's see, let's go back here. Nothing is there at 13. So 6 is B. So the children of 6, 12 and 13 are addresses, but there's nothing there, right? You can talk about an address on a street, a theoretical address, but there doesn't have to be anything at that address. So there's nothing at this address here. So I can keep going with, 14 gives me C, 15 gives me DE, 30 gives me D, 31 gives me E. And if I were to ask for anything else, I'm at the end of the road. There's nothing else for me to see. There's nothing else from here. So we can use numeric addressing this way. We'll get used to this as we start working more and more with this. So when we are storing information as text with double quotes, this is actually we call this a tape. It's one of the string types in Hoon. This is actually a string of it's a bunch of characters in a cell that goes to the right. All right, so this is a tape. It is a list or a collection of cells. And if I were to do something like ask it what is the thing at address 2, it is I. If I were to ask it what is the thing at address 3, it would let me refer to am the very model of a modern major general. Right? It would let me refer to literally everything else in what's going on here. So we're going to use this kind of navigation occasionally when we work with it. It is more common. Well, okay, I should give you the other less common one first. The less common one is to use head and tail notation, which is the positional notation. So you'll notice that if I give it a minus sign, it gives me the head. If I give it a plus sign, it gives me the tail. If I want to go more in depth, like I get the space here, then I get the tail, and then I get the head of the tail. It's a little bit weird for people seeing this for the first time because it alternates pluses, minuses, and left and right. I think it does make it readable in the long run, but it's a weird thing to get used to here. So it's Hoon. Unfortunately, the more intuitive way for most people would probably be to write it like this, like less hep, and just do left, right that way. But that's what we have. And then there's named positions as well that I can't access directly here because a tape, a list of characters doesn't have internal names for things. So I can only use positional and numeric addressing and grabbing things inside of it. All right, there are going to be some soft exercises in the notes that you should complete. Let's take a look at a couple of those right now, just so we're used to addressing. One of them is the fruit tree. So for instance, what is the address of the grapes in the fruit tree? So you can compare to another chart if you want. Yeah, so the grapes are at address 9. So we can say 1, 2, 3, 4, 5, 6, 7, 8, 9. Get it here. 10, 11 gets us to the banana. 12 gets us to the watermelon. 13, 14, 15 to the apple. I left 16, 17, and 18, and 19 blank. 20 gets us to this child here that has the head as the peach, and so forth. Okay, so take a look at these, and then you'll also be able to write the positional notation for both of these, and it'll get you used to like how do you find something? How do you actually locate something inside of a Hoon expression here? All right, more to do with trees. That's great. Let's talk about cores, because we are going to love cores. We are going to use cores for everything. And right now you're saying to yourself, what on earth is a core? Okay, so there's a question here. I guess this is talking about like addressing, like locating things. Why would we do this? Is that your question? Yeah. So in any case, so this is how a list is implemented. Okay. So a list is values in order, and then there's a by convention, there's a null blank at the end, or there's an empty element, a sig at the end that does this, but this is a list. There's a more commonly seen sugar syntax for it to put the sig before, because you're marketing as a list when you think about it, but this is a list. Okay, and yeah, and so there are the fact that it's a binary tree that branches rightward. It's not like actually occupying the parts of the binary tree that are empty, right? So we're just talking about things that are addresses. So here, if we're storing a tape, yeah. So Jack's talking here. Jack, do you want to unmute and talk about that for a second?
Yeah, so basically, like, if you have, let's say I'm looking for a word in the dictionary, right? So one thing I could do is look through every page of the dictionary until I find that word. But if that word is zebra, it's going to take me a very long time, right? So that's kind of like what you're doing when you're looking through a list, if you stored all your data in a list. But if you know a strategy, if you say, okay, I'm going to crack the dictionary in half. Is zebra going to be on the left side or the right side? And then if it's going to be on the right side, okay, now I can just search that half, and then I can just crack it again, and then do the same thing until I find where the word is. And that's going to take me log n, where n is like the number of pages, which is a much smaller number than n, which is a strategy where you just look at every page until you found it. Does that make sense? Like, this is in computer science, like, it's storing things in a binary tree is like super common for this sort of reason.
Yeah,
And
so it's
okay.
optimized sort of for time concerns rather than space concerns. Is that right?
Well, I think if you're storing something in a list versus a binary tree, it's the same amount of space, right?
Can you use this addressing system to create loops like we did before, but rather than having the bar hep as a kind of reference point to restart the loop, you could like give an address location to restart a loop?
So that is an extremely interesting question. The short answer is that is basically what Nock is doing when the Hoon compiles to Nock. The more involved answer is that you could manually implement something like that in Hoon, and there are cases when we're going to do it different ways, but it's kind of uncommon to do it because it's easier to just mark something with a trap or something like it and just say return to that point. When we get deeper into cores, you'll also see what Sentiz is doing, the reset rune is doing, is something similar to what you just suggested. Like, what's actually happening is we are looking up the name of something and replacing the values inside of that thing. So you're close to the truth with that question. Yeah, so this example here, it's not actually storing hello, lo, lo, o. It really is just storing HELLO sig. It's just that we have different ways of accessing the components of this. Right, like this is the, well, hello isn't gibberish, is it?
Oh, no, he had a question about like, can you see the tree for an arbitrary generator, an arbitrary piece of Hoon code?
Oh, yeah.
That's really what happens when you input it into.
I mean, in a sense, yeah. Let me see here. Let me go back to Tmux. I mean, like in a sense, if I actually look at well, let's stare into the white hot core of Hoon here. All right. This is great, actually, because this is perfect, because I did want to talk about cores right now. All right, so a core is one of the key organizational ideas that we're going to use in Hoon, and you're going to work a lot with cores. But what a core is fundamentally is a cell of what we're going to call, we'll just call it code and data for now. We use different names internally, but we basically have a cell of code and data. And so the head of anything that is a core is code, which ultimately is knock code. And the tail of anything that is code is the data that that code can evaluate with, which includes the arguments to it. So if I take a name like add, and I take the head of add, and it spits out to me a bunch of knock expressions here that's telling it how to do whatever it is that it does. This tells you at least one thing. It tells you that add is a core in the sense that I was talking about. But what did I call add when I talked about add before? Right, I called it a gate. So a core is kind of the super concept that unifies traps and molds and gates and a lot of other concepts inside of this. It's kind of like an object in an object-oriented language. Not exactly the same thing, but it's always going to be a pair of code and data. So if I want to look at the code in add, it's already been compiled to knock. So when I look at it, I see the knock. And so this is what's going on here. So the question here is, do you just see trees? So you actually don't, well, you think about the head and the tail of things a fair bit. And you think about like the head of the head or this kind of operation somewhat less frequently. You often don't have to go deep into a tree to figure out what's going on because you can name the things in the tree. You do have to think about rune children, but you can name the things in the tree. So by far, it is more common to not figure out. So add actually has an address in the Urbit space, and I could try and figure out what that is. And I could invoke add directly in the Urbit operating context by figuring out what the address is. I don't want to do that because that's a total pain and I don't want to find that thing. So I have a name for it and I'm just saying use add, right? Go to Jack's house. This is add, right? We're going to use add. But now that I have add, I can talk about the head of add, which is the code of add, or I can talk about the tail of add, which is everything that add knows about. So what does add know about here? It knows about its inputs, and it knows about what we're going to call the context, right? Which is like everything else. So it knows about other parts of Hoon. And it knows that it's running in Hoon version 139. And then these are shorthand for the pretty printer for like whatever else it knows about. So like add would know, it doesn't need to know about subtraction, but it knows about subtraction. Like it's at the same level of the operating system. Yeah. So when I tell you everything in Urbit is a binary tree, I am not exaggerating. Everything is a binary tree. And every lookup you do, everything you do is a binary tree, which is why we're talking about it, right? This is why this is this fundamental idea. So we are going to use cores an awful lot. And I will tell you right now that the idea we are going to work hardest on you understanding over the next couple of weeks is the core. Because when you understand the core, you will understand Hoon. You won't know all the runes. You won't know how to do everything inside of it, but you will understand the nature of Hoon and why Hoon works the way it does. So this is the most important structural concept for you to understand in Hoon. So it's always going to be a pair of the operating code and then whatever data that operating code receives. And when we talk about calling Urbit, sometimes they call it in the docs like a subject-oriented programming language. What that refers to is the subject is basically like this. It's where the core evaluates. It's the thing the core knows about when it evaluates the code. All right. It's really neat. So when we're writing a generator knows about the sample, the input values that it receives, and it knows about basically the standard library of Hoon. And if you want to do anything else, you're going to have to import a library to do something else. Like we used, if you went through the notes last time, there was that library which was numbers to words. So we could import that inside of a generator file, and then you would be able to use everything from it inside of that generator file. All right. So anything that starts with a bar is a core. All right. So what are things we know about right now that start with bar? Any rune? All right, so we know about bar tiz, which is a gate. And we know about bar hep, which is a trap. And I don't think we know about any others at this point. There are others. So we are going to get deeper and do more with these. And so when I write a core, what it's going to look like is this. Barsen is a new one. So let me go ahead and write Barsen over here. Barsen is going to be the last big concept we're going to introduce today. And it's one I'm like, you're going to chew on it for a while, because like I say, this is the big thing. Okay. And we're going to, like I said, we're going to keep cycling back to this. So a Barsen starts a core, and then we're going to define what we're going to call arms, but are basically like the things that it knows about in the core. So we're going to define an arm, which is add one. So it has a name, add one. That's the positional address. This is Neil's house. This is Jack's house. And then it has an expression inside of it. And this expression is another core. Yeah, a core is similar to a class in some ways. Don't lean too much on that analogy, but it plays the same sort of role in Hoon that a class plays in a language like C++ or Java or Python. So each one of these arms contains its own core, which happens to be a gate. And you should be able to read what these are doing. So add one returns, it accepts a PAT-UD. It is going to return a PAT-UD, and it is going to add one to that value. Sub one is going to do these other things and work this way. Right now, I'm going to call this my core, and I'm going to try pasting it in Dojo and see if Dojo's happy with this. All right. So I just pasted it in Dojo. I used the tiz my core, and then I pasted everything here. And so now I can say, if I want to refer to one of these, I remember if I use the parentheses, so add one will be resolved against my core. So it's going to look inside of my core for a name, add one. And it finds it, and it changes that value. And if I want to subtract one, then I can look up sub one inside of my core. If I don't give it a subject, a core to resolve that name against, Dojo tells me, I don't know what that is. I don't know where to find that. So it has to have a search path. This goes back to, this is like, we have a lot of jacks in Urbit, so I'm talking about the Tamlet Modnice jack. I have to resolve the name against some context for you to get this right. So this is what I'm doing here with this colon, is I'm resolving the name add one against the core that I defined with the name my core just before this. So when we write generators, we are going to be able to include arms and write things like this. Let me do one of these real quick. And save this. So add one.hoon. All right. Bar commit base, and then we'll go ahead and wrap for today. All right. So what this code is doing here, it's a gate, and then it's got this Tisgal thing. That's a new rune, but basically it composes two expressions together. So this is the expression that gets evaluated, but it means that it also knows about this other branch. So it lets us basically put two things next to each other. Let me see if I can. Yeah, so it's just a way of situating two code expressions next to each other. So here what I've done is I've been able to define add one inside of a bar sen inside of a core, and then use it and return that value out of my generator. Kind of like having a library that I just built right there. We're going to do a lot more with libraries and play with these later on. But this is this big idea that you're going to sit on, you're going to chew on for the next week. And when we come back, you're going to have questions for me, because this is the thing to start getting comfortable with now as you think through this and understand this.